So, welcome to this continuing lecture on dimensional analysis, where we are now going a little bit deeper and trying to understand the meaning of all these dimensionless groups that arose when we were doing dimensional analysis. As you recall, we did the dimensional analysis for the heat transfer across a surface of a heat exchanger, and we got a relationship between these quantities, the Nusselt number, the Reynolds number, the Prandtl number, and so on. A considerable reduction from the complexity of the original problem, without a doubt, but still we still do not have a good idea of what these things called Reynolds number and Prandtl number mean. In the mass transfer problem, we had a mass flux, the Sherwood number, dimensionless mass flux, a function of the Reynolds number and the Schmidt number. And if you recall, when we looked at the transport, we had a power number which was a function of other dimensionless groups, the Reynolds number, the Froude number, and so on. And I was trying to give you some idea of what exactly these dimensionless groups mean. Two broad mechanisms of transport that we will be considering in this course. The first one is convection. Convection is transport because material is carried along with the fluid flow, because energy is carried along with the fluid flow, momentum is carried along with the fluid flow. Okay. The flux, the convective flux of material transported across the surface per unit area per unit time. Okay. That is just equal to the density of the quantity, mass, momentum, or energy, the density of that quantity times the velocity perpendicular to the surface. Okay. So, the mass density times the velocity, that is the concentration times the velocity, the energy density times the velocity, and the momentum density times the velocity. Okay. That is convective transport. Diffusive transport, on the other hand, okay, is basically a transport due to molecular velocity fluctuations, which takes place even when there is no fluid flow across the surface. Okay. Even when there is no fluid flow across the surface, material, energy, momentum will still be transported across the surface because the fluctuating velocity of the molecules, okay, which carry along with them, okay, the material. There will be a net transport of material only if there is a difference in the concentration or temperature across that surface. If there is no difference, then what goes up will be equal to what comes down due to molecular fluctuations. There will be no net transport. When there is a difference, for example, when the concentration below is higher than the concentration above, then the molecules from below will carry a higher concentration along with them. Molecules from above will carry a lower concentration. Therefore, there will be a net transport of mass across the surface. Similarly, if there was a temperature difference, the energy of molecules going up will be higher than the energy of molecules going down. Therefore, there will be a net transport of energy. The same thing holds for momentum. If there is a net flow tangential to the surface, molecules going above will have a different momentum than those going down. So, diffusive transport basically depends upon the difference in concentration across the surface, or more particularly the gradient in the concentration, variation in concentration with respect to length across the surface. Okay. And the rate of transport of all of these due to molecular fluctuations can be written in this common form. Okay. For any quantity, the rate of transport of that quantity per unit area per unit time is equal to a diffusion coefficient times the gradient in the density of that quantity. Okay. Density of that quantity per unit volume. The gradient of that gives you one more inverse length scale. Okay. And if you put those two together, this diffusion coefficient for any quantity has to have dimensions of length square per unit time. So, we had expressed the Fourier's law, Fick's law, and Newton's law in terms of this. Okay. And what we had got was diffusion coefficients for mass, momentum and energy. Okay. I have interchanged these two here, my apologies. This should be Fick's law. Okay. And this one should be Fourier's law of heat conduction. Okay. And these things here are the diffusion coefficients. Okay. Now, when we do dimensional analysis, if we want to find out what is the dominant mechanism of transport, we have to find out the ratio of convection and diffusion. Okay. So, for example, for momentum, the ratio of convection and diffusion, okay, ratio of convection and diffusion, I told you that convection of momentum will go as the velocity times the momentum that is being carried along with the flow. Okay. So, this will go as the velocity times the momentum which is being carried along with the flow, which is just the momentum density itself. Okay. Okay. So, that is the convective effect, okay, the momentum density times the velocity. Okay. Diffusion, okay, it goes as the kinematic viscosity times the momentum density divided by a length. Okay. So, nu into rho u by a length. Okay. So, the ratio of these, okay, will just be equal to u L by nu. The ratio of these will be just equal to u L by nu, the ratio of convection and diffusion. Ultimately, it will not depend upon the quantity that you are considering, okay, because that is there both in convection as well as diffusion. The density comes in both. Okay. Now, the kinematic viscosity is equal to the ratio of viscosity and density. So, if I write this way, okay, I get rho u L by mu. As you will recall, this is our familiar Reynolds number. Okay. So, the Reynolds number actually is just a ratio of momentum convection divided by momentum diffusion. Okay. Now, if I wanted to do this for mass or heat, all I need to do is to change, okay, for mass transfer, for example. Okay. I just need to change this to a concentration. Okay. Instead of the momentum density, I will have the mass density. Okay. So, that is a concentration, and then instead of the momentum diffusivity, I will have the mass diffusivity. Okay. And therefore, this is just equal to u L by d. Okay. This goes by the name of a Peckley number. Okay. For mass diffusion. Okay. The same thing I could do for thermal diffusion. Okay. In that case, the concentration has to be changed to the energy density. Okay. I have to change for thermal diffusion. I have to change the concentration to the energy density. Okay. And I have to change the diffusivity from mass diffusivity to the thermal diffusivity. Okay. And therefore, finally, I will just get, instead of u L by d, I will just get u L by alpha. Okay. That is a Peckley number for thermal diffusion. Okay. So, these are the dimensionless numbers that are ratios of convection and diffusion. Okay. You could also have dimensionless numbers which are ratios of two diffusivities. Okay. How would that look? Okay. If I take the ratio of momentum by thermal diffusivities, okay. The momentum diffusivity was the kinematic viscosity nu. The thermal diffusivity was the thermal diffusivity alpha. Okay. I can express that back in terms of the original quantities. This is mu by rho. If you recall, the thermal the momentum diffusivity is the kinematic viscosity, ratio of the viscosity and the density. The thermal diffusivity was K by rho Cp. Okay. When I had expressed it in terms of the energy density, okay, the thermal diffusivity was K by rho Cp, and this gives me Cp mu by K. Okay. If you recall, when we did the heat transfer problem, this was the Prandtl number. Okay. So, the Prandtl number is the ratio of momentum diffusivity and the thermal diffusivity. Okay. You can take the ratio of momentum diffusivity and mass diffusivity. Since all diffusion coefficients have the same dimensions, you can take ratios of each of them against the other, and all of those will end up being dimensionless groups. Okay. So, this will turn out to be mu by rho divided by the mass diffusion coefficient. Okay. Basically, that is equal to nu by the mass diffusion coefficient, the kinematic viscosity. So, you get mu by rho d. Okay. And if you recall, when we did the mass transfer problem, okay, that was what was called the Schmidt number, okay, mu by rho d. Okay. Okay, I had written this in terms of mu by rho d. Okay, use the inverse instead of the rho d by mu, and that ended up being the Schmidt number. Okay. So, once we understood these fundamentals of convection and diffusion, all of those dimensionless groups that we had can be classified into a few fundamental forms. Okay. One is, of course, the dimensionless fluxes. Okay. As I said, these dimensionless fluxes emerge from a relation of this kind. Rate of transport of material is equal to diffusion coefficient times the change in density divided by a length. Okay. So, the dimensionless fluxes in this case, okay, for mass transfer, okay, will just turn out to be J by d delta C by L. Okay. Because I know that d times delta C divided by a distance has to have the same dimensions as j. Okay. So, j by d delta C by L will be a dimensionless group. Okay. So, that is the Sherwood number. For heat transfer, this will be q by k delta T by L. Okay. That is the Nusselt number. Okay. Because from Fourier's law of heat conduction, q by k delta T by L has to have the same dimension. Okay. It has to be dimensionless. Okay. I could also express it in terms of the energy density and the thermal diffusion coefficient. Okay. You can easily verify that this can also be written as q by alpha delta T by L, okay, for heat transfer. I am sorry, delta E by L. Okay. A diffusion coefficient times the difference in the density of the quantity divided by the cross stream distance or the gradient, okay, in that direction. That is the Nusselt number. Okay. And for momentum transfer, okay, you would think that the stress could be scaled by the kinematic viscosity, the diffusion coefficient, times delta of rho u by L. Okay. This is not what is usually used. Okay. What is usually used is a friction factor or a drag coefficient. Okay. And there, rather than using the viscous effects, what is usually done is to use the inertial effects. Okay. Okay, rho u square by 2. Okay. Because as I said, the transport of momentum across a surface is equal to the velocity times the momentum density. The convective transport, okay, across a surface is equal to the velocity times the momentum density across that surface. Okay. So, the convective transport rates are usually used in correlations. Okay. The velocity times the momentum density is used to scale the stress, and these are what are called the friction factor or the drag coefficient. Okay. So, that is a dimensionless flux, that is the dependent variable. Okay. What are the independent dimensionless parameters? They are of two types. One is ratio of convection by diffusion. Okay. Ratio of convection by diffusion. In the case of mass, momentum by mass, okay, in the case of mass transfer, okay, that turns out to be UL by D, okay, that is a Peclet number. In the case of heat transfer, that turns out to be UL by alpha, which is a Peclet number for heat transfer. And for momentum transfer, it is UL by nu, which is equal to rho UL by mu, the Reynolds number. Okay. So, these are ratio of convection and diffusion. Okay. And then of course, you have the ratio of diffusivities. Okay. Momentum by mass diffusion is equal to nu by d is equal to, okay, which is a Schmidt number. Okay. And momentum by energy, okay, which is equal to nu by alpha is equal to Cp mu by k, okay, which is a Prandtl number. Okay. And these numbers are all interrelated. Okay. So, for example, the Peclet number, okay, I can write it as, okay, the Peclet number for mass transfer, okay, will be equal to UL by D. Okay. I can write it as UL by nu into nu by D. Okay. You can see that nu and nu cancels out. So, that is the Peclet number. This UL by nu is the Reynolds number and nu by D is the Schmidt number. Okay. Therefore, the Peclet number for mass transport, okay, is just equal to the Reynolds number times the Schmidt number. Okay. Similarly, the Peclet number for heat transfer is equal to UL by alpha, which is equal to UL by nu into nu by alpha. Okay. is equal to the Reynolds number times the Prandtl number. Okay. So, these are all related. Okay. So, therefore, I have broadly classified the dimensionless numbers that we came across as dimensionless fluxes, ratios of convection and diffusion, and ratios of diffusivities. Okay. And you can see that this encompasses all of the dimensionless groups that we had almost. Okay. In the case of the heat exchanger problem, all of the groups are included here. The Nusselt number is the dimensionless flux, Reynolds number, ratio of inertia and viscosity, ratio of momentum and convection and diffusion. Prandtl number, ratio of momentum diffusion and thermal diffusion. Okay. In the case of a heat exchanger, okay, apart from the ratio of lengths. Okay. In the case of mass transfer from a particle, okay, the Sherwood number, dimensionless flux, the dependent variable, function of Reynolds number, ratio of momentum, convection and diffusion, Schmidt number, ratio of momentum diffusion and mass diffusion. Okay. So, all of these are classified just based upon ratios of convection and diffusion. Okay. The power number that we had earlier is a ratio of the power and the momentum convection. Okay. Rho d power 5 omega cubed is a momentum convection because it contains the density. The momentum is proportional to the density times the velocity. Okay. Had I scaled it by viscous scales, it would have been ratio of power and momentum diffusion. Okay. But since I have done it this way, as it is commonly done in momentum transport, it is common to scale by inertial scales rather than viscous scales. Ratio of momentum of power and momentum diffusion. Function of the Reynolds number, ratio of momentum convection and diffusion. The Froude number, the ratio of momentum transport to the acceleration due to gravity, and we also had a Weber number, okay, which was basically ratio of inertia and surface tension. Okay. So, in momentum transport alone you have some additional parameters. Okay. Okay. Okay, some additional dimensionless groups for momentum transport. Okay. In case gravity is important, okay, you can have an additional term which goes as the Froude number, okay, u square by GL. Okay. You can see that this is dimensionless. Okay. Length square per time square in the numerator, length square per time square in the denominator. Okay. So, where gravity is important, you will have numbers that represent the ratio of gravity and the inertia and the acceleration due to gravity. Okay. In cases where surface tension is important, okay, you could have additional numbers. Okay. Surface tension, you could scale it either by viscosity, okay, in which case the dimensionless group will be equal to mu u by gamma. Okay. You can verify that this is dimensionless. Okay. It is called a capillary number. Okay. Okay. Surface tension by inertia, okay. We had just got the Weber number in the previous example where we had expressed it in terms of the frequency, okay, the angular velocity. Instead, if you express it in terms of a linear velocity, you will get rho u square L by gamma. Okay. This is called the Weber number. Okay. And there are other such numbers, dimensionless numbers, which represent different effects in the case of momentum transport. Okay. So, in this lecture I have tried to give you a fundamental understanding of what all of those dimensionless numbers mean. Okay. One category is the dimensionless flux. Okay. The flux scaled by the diffusive scales in the case of mass and heat transport. It is conventional in momentum transport to scale it by the inertial scales. Okay. So, in the case of mass and heat transport, scale it by diffusion, you get the Sherwood number, Nusselt number. Momentum transport, you scale it by convection and you get the friction factor, drag coefficient. These are the dependent variables, the average flux that you want to calculate of mass, momentum, energy. These depend upon ratios of convection and diffusion. Okay. The Peckley number for mass and heat transfer and the Reynolds number for momentum transfer, ratios of convection and diffusion. And the other independent variables are the ratios of two different kinds of diffusion. Okay. Momentum to mass is what is called the Schmidt number, momentum to energy is what is called the Prandtl number. Okay. And these ratios of convection and diffusion, the Peckley numbers, can be expressed as the Reynolds number times the Schmidt number or the Reynolds number times the Prandtl number. Okay. And these encompass all of the correlations that I had got for you earlier. Okay. Now, why do these correlations have these specific forms? Okay. Why do the correlations? Okay. Beyond this we cannot do by dimensional analysis, but we can still get some idea of why these correlations have these specific forms. What do the forms of the correlations depend upon? Okay. What are the factors that affect which correlation is applicable in which limit? Okay. Both for mass transfer and heat transfer. Okay. For heat transfer I told you that you would get different correlations depending upon whether it was laminar flow or turbulent flow. Okay. Okay. And then in the mass transfer I told you will get different correlations depending upon whether the Reynolds number and the Schmidt number are small or large. Okay. Why is it that you get different correlations in different regimes, and what determines, okay, what are the factors that determine what correlation you will get in what system? Okay. We will try to take a closer look at that in the next lecture. Okay. So far I have tried to explain things to you in terms of ratios of convection and diffusion and ratios of diffusion, trying to give you a unified framework for how to understand the transfer of mass, momentum and energy as diffusion processes. Okay. The fluxes are related to a diffusion coefficient times the change in the density of that quantity divided by a length, or the gradient of that quantity, okay, of the gradient of the density of that quantity. Diffusive flux. Convective flux is just equal to the velocity times the density of that quantity. If you take the ratios of those two, you get dimensionless numbers, which are ratios of convection and diffusion. You could also get dimensionless numbers that are ratios of two different kinds of diffusion. Okay. Next class, what is it that determines the form of these correlations? We will take a slightly deeper look at that and try to classify these. Okay. Can I get some limited set of correlations which are applicable for a large number of systems, and what is it that determines what that set is? Okay. I will do that with respect to mass and heat transfer. Okay. In the next lecture I will limit it to that. Momentum transfer is slightly different. I will come back and explain what are the sophistications that are involved in problems of momentum transfer. So we will continue that in the next lecture. Okay. I hope I have given you some fundamental understanding of how we are going to approach problems as we progress using just dimensional analysis. Once we complete dimensional analysis, I will show you how to solve problems at the local level, and from that reconstruct what the large scale transport rates are. That will be the program of the rest of this course. We will see you in the next lecture.